Hello and welcome to the Callum Cymru revision session for A-Level Further Maths. My name is Matthew McMillan. I'm a teacher at Christ's College in Brecon, and today we're going to look at solving first order differential equations. So there are a number of elements to the differential equations part of the specification. In this session we are just going to look at solving first order differential equations. We are going to look at using an integrating factor, but also what an integrating factor is and what it does. We're also going to look at the format that we want our differential equations to be in. We want them to have a dy over dx at the front, and then have a think about what to do if we don't have that format. At the end, I have a question involving modelling, involving some raindrops, and we'll leave the second order differential equations for another session. So we'll start off with a straightforward differential equation. A first order differential equation basically has a dy over dx in it, and this question is more like one you'd get in your normal maths course. So find the general solution of dy by dx equals 4xy. What we want to do is we want to separate the equation up. So we'll keep the dy on the left hand side, and we'll keep the 4x on the right hand side. And then what we'll do is bring the y to the left hand side, so that's 1 over y, and we'll bring the dx to the right hand side, and then we'll put an integration sign in front of them, and we'll integrate both sides. So we're integrating the left hand side with respect to y, so that's giving us natural log of y, and we're integrating the right hand side with respect to x, so that's giving us 2x squared. Now, we would get a constant. We could say that we're getting a constant on both sides of the equals sign, but maybe we should just lump it together because a constant is just a number. We'll just put it as a constant on one side. We'll try and get rid of the natural log, so we'll take e of both sides, so we get e to the power of 2x squared plus c. Maybe it'd be nice if we just thought about this bit here. That's e to the power of 2x squared times e to the power of c. And if we let e to the power of c equal a, we can rewrite this in a different format. So our final answer here would be y equals a e to the power of 2x squared. Okay, so that's a straightforward first order differential equation, more like one you'd get in your sort of normal maths course. Okay, so this diagram shows the family of solutions. I've put the equation in y equals a e to the power of 2x squared. Basically, as we change a, the curve could look slightly different. I've selected just kind of randomly that we could have a is equal to 2, 1, 0, minus 1 or minus 2, but you could see a could take basically any value, so that's called our family of solutions. Okay, so this is more like the type of question that you might expect to get, a non-separable equation. You can see the x and the dy over dx are kind of implicitly linked, so we're not going to be able to separate this out. And to approach this, what we want to consider is what rule does this look like? So I'm going to just bring up the product rule, because that's kind of where we're heading with this. I can kind of see that if I differentiate this u, I get du over dx. So if I differentiate the y, that takes me to the dy over dx. And if I differentiate the v, that takes me to the dv over dx. So if I differentiate the x, that should take me to, well, I guess in this case it would be a 1. So I feel like I can combine this bit at the top. Thinking about it as the product rule, I can see the u and the v come together. In my example here, the u and the v would be, well, it could be the y and it could be the x, so we're going to combine those two bits. So let's bring it together, and we get d bracket xy over dx equals x cubed. And now we're good to go, and we can apply the same techniques as before. So I'm going to bring the xy, I'm going to integrate the left hand side, and we're going to integrate the right hand side with respect to x. That gives us 1/4 x to the power of 4 plus c. Okay, now that's a really straightforward example. Are you unlikely to get something that straightforward in your exam? But that's the technique that we're using. Okay, so we've just got one more example here. Let's just check. So our derivative of y does take us to the dy over dx, and the derivative of x would take us to the number 1. So this looks like another situation where I can apply the product rule in reverse. So we're going to get dxy with respect to what x equals e to the power of 2x, and then we're going to integrate both sides, so we get xy equals the integral of e to the power of 2x with respect to x. Xy then will equal 1/2 e to the power of 2x plus c. Again, another straightforward example, and you should be happy doing questions like that. Now, in the previous two examples, we could see that the product rule could be applied straight away. Whereas here, we have one that is not exact. So if we did differentiate the y squared, that would take us to 2xy. That is not appearing here. So we're not going to be able to apply the kind of reverse of the product rule. What we're going to do is we're going to times everything here. I'm going to times everything here by 2x. And this bit by 2x, and also this bit by 2x. That's going to give me 2x squared y dy dx plus 2xy squared equals 6x squared. Now this is looking a little bit better. If I do differentiate the y squared, this bit here, that's going to give me 2y and the dy by dx. And also if I do differentiate the x squared here, that's going to give me the 2x here. So it's looking like we can now apply the reverse of the product rule. We get the derivative of x squared y squared with respect to x equals 6x squared. So if I integrate both sides, that gives me x squared y squared equals 2x cubed plus c. Now, the numbers that I chose here, these bits here, 2x there, that is called an integrating factor. On this one, I've chosen it because I know that it's going to work, but we don't want to just guess and use intuition. What we want to do is we want a method for finding the integrating factor. So that's what we're going to take a look at, a method for actually how we find the integrating factor. Okay, so let's have a look at how we find an integrating factor. We aren't just going to guess, we are going to use a method. It's important to note that this method is only going to work if we have a single dy by dx on its own. Otherwise, this method is not going to work and you need to rearrange it to get it into this format. So our integrating factor, we looked at it just now, you are timesing by some kind of function, and we're going to call that function f of x. That is going to give us then f of x dy over dx plus f of x times px y equals f of x times q of x. Okay, so we've got various different functions here. We've got our kind of original functions, and then we're multiplying by f of x. The situation that I want is I would like it to be so that f of x here will differentiate to take me to fx px, so this bit here, and I want the y to differentiate to take me to this bit here, dy over dx. Okay, so that's what I'm thinking about. Now y differentiates to dy over dx as it is, so I kind of can park that there. What I'm in fact, I'll just write on there differentiate okay, that's what we're trying to get. So what I'm going to do then is I'm going to take f of x and differentiate it. That gives me f dash x, and that should equal then the bit on the right hand side, which is fx p of x. Let's do a little bit of rearranging. If we get f dash x and divide by the f of x, and then we're going to keep the px over on the right hand side. You'll notice on the left hand side this looks very much like a log integral, so I'm going to actually write integral and then dx, and we're going to do the same on the right hand side, so we're going to integrate both sides with respect to x, and that's just because I'm looking at this left hand side and I'm seeing f dash x over fx, so I know that that is going to integrate to the natural log of f of x, and that equals the integral of px with respect to x. Now if I want to get rid of the natural log element, I take e of both sides, so f of x equals e to the power of the integral of p of x with respect to x. So our f of x at the start is given by e to the power of the integral of px with respect to x. That is the integrating factor. Okay, and we'll have a look at an example and using one now. Okay, so let's have a go at solving this using an integrating factor. Solve dy over dx plus 3y equals e to the power of 2x, and we've been given some initial conditions as well. Now, looking at what we were looking at previously, our function here, p of x, that is the number 3 in here. So px equals 3. That means that our integrating factor, f, will equal e to the power of the integral of 3 with respect to x. Well, that equals e to the power of 3x. So that's our integrating factor. So I need to multiply everything here by e to the power of 3x. That's going to give me e to the power of 3x dy over dx plus 3 e to the power of 3x y equals, so we've got e to the power of 2x, and I'm times it by e to the power of 3x, so I'm kind of adding the powers, e to the power of 5x. Okay, so I've times through everything there, times by e to the power of 3x. Now we're looking at using the reverse of the product rule, or combining the bits together. So we know our y, using our method, the y should be turning into the dy over dx, and then the bit here, the e to the power of 3x, that should be turning into the 3e to the power of 3x. So that's going to give us d bracket y e to the power of 3x over dx equals e to the power of 5x. If we integrate both sides now, we get y e to the power of 3x equals 1/5 e to the power of 5x plus c. Because we've been given some initial conditions, we should use them. So when x is 0, y, it says, is 6/5. So that gives us, what's that going to be? So it's going to be e to the power of 0, so that's going to be 1. So we get 6/5 here equals, and then x is 0, so it's e to the power of 0, so we get 1/5 plus c. That gives us then c equals 1. So our final equation y is y e to the power of 3x equals 1/5 e to the power of 5x plus 1. We could divide everything through here by e to the power of 3x. So if we did that, that would, and we take away the powers, remember, so we're going to get y equals 1/5 e to the power of 2x plus 1 over e to the power of 3x, so e to the power of minus 3x, if we wanted it to look a little bit nicer. So that's a straightforward question involving finding the integrating factor and then solving using the integrating factor. So we'll just look at one more example before we have a go at an exam question. Find the general solution to sin x dy over dx plus 2y cos x equals cos x, and we're going to need to find an integrating factor. In this one, it's important to notice that it's not in the correct format. We need a single dy over dx on its own, and we do not have that here. We've got sin x next to it. So what we're going to do is we're going to divide everything here by sin x. That should give us the correct form. If we do that, that's going to give us dy over dx plus 2y cos x over sin x equals cos x over sin x. I could change them to cot, but I'm just going to leave them as they are for the time being. So let's think about our integrating factor. So integrating factor, that's going to equal e to the power of the integral of, it's the 2 and the cos x sin x bit. So 2 cos x over sin x with respect to x. Because the function that we've got here is the derivative is on top. So if you differentiate sin x, you get cos x. That means we've got a log integral. So we're actually getting here e to the power of 2 natural log of sin x. That then we could bring the 2 up as a power, so we get e natural log of sin x squared. And if we have e to the natural power of a natural log, they kind of break each other up and we get sine squared x. Okay, so that's going to be our integrating factor. So let's multiply through by that. So multiply by sine squared x. That's going to give us sine squared x dy over dx plus 2y, I guess because you've got a sine squared and you've got a sine x on the bottom, we're actually going to get 2y sine x cos x. And we're going to get a similar thing happen here. We're going to get a sine x cos x, because the sine squared is going to cancel with one of the sine x on the bottom. So we're kind of looking here at the sine squared. Hang on a sec, where's my right colour here? So the y differentiates to dy over dx, and the sine squared x, that should be differentiating to the 2 and to the sine x cos x bit. So if we group them together, we should get the derivative of y sine squared x with respect to x equals sine x cos x. If we then integrate both sides, we get y sine squared x equals the integral of sine x cos x with respect to x. This bit on the right hand side is not particularly nice to integrate as it is, so we're going to combine the sine x cos x using our double angle formula, and we get a half sine 2x. That is a little bit nicer to integrate. And if we integrate that, we should get y sine squared x equals -1/4 cos 2x plus c. Okay, so that's a slightly harder one. Firstly, because you have to make sure that your question is in the right format. We had a sin x here and we didn't want it there. And then it's a little bit more awkward dealing with the trig functions. Let's have a look at an exam question on this topic now. Okay, so this is a fairly typical exam style question. 8 marks, and it's a nice 8 marks to get if it comes up. We notice that we have a cos x in front of the dy by dx at the beginning, so my first step will be to get rid of that. I'm going to divide through by the cos x, so that gives us dy over dx plus y tan x equals 2 cos squared x sin x plus 1 over cos x, so sec x. Now this is in the format that I would like to find my integrating factor. So let's just do that over here, integrating factor. And we're going to do e to the power of the integral of whatever this bit here is. So that's tan x with respect to x. Now the integral of tan x is in the formula book, so we get e to the natural log of sec x. And the e to the natural log breaks itself up, so we just get sec x. So our integrating factor is going to be sec x, so let's times by sec x. So we get sec x dy over dx plus y sec x tan x equals, now sec x is the same as 1 over cos x, so this is going to give us 2 sin x cos x plus sec squared x. I decided to view the sec x as 1 over cos x for this part here, because it gets simplifies the cos x bit for me, and I decided to keep the sec as sec for this part here, because I noticed that these two, that bit is in the formula book. That's a standard integral, and then 2 sin x cos x. I also know that that's going to, using the double angle formula, that will collapse to sin 2x. So now we've got the format that we would like. We can say that using the sort of reverse of the product rule, we're going to get the derivative of y sec x with respect to x is equal to, and this is where I'm going to collapse this here, that's equal to sin 2x plus sec squared x. And now we can go ahead and integrate this, so we get y sec x equals, and now this is a nice form to integrate in, so we're going to get minus a half cos 2x, and then sec squared goes to tan x plus c. Now, I just want to double check what the question says, because at the very beginning it says find it in this format, y equals f of x. I do not have it in that format at the moment, so I just need to divide through by sec x. Now, it's not saying it wants it simplified or anything, so we could, because dividing through by sec x is just the same as timesing by cos x, I could just times everything through by cos x. So this would give me minus a half cos 2x cos x plus tan x cos x plus c times cos x. And I just need to be careful that I'm multiplying that constant by cos x as well. And that answer there would be acceptable for our final solution. Okay, so we have another question. This one's given with a little bit more context, and it's about a raindrop falling from a cloud. I noticed that it says the raindrop falls from rest from a cloud, and it talks about the velocity is v and the time taken is t. So it must be travelling at 0 meters per second initially, and I guess our initial time would be t is equal to 0. And I'm just double checking here. T is allowed to equal 0. That might come in handy later on in the question. I want to start with, I'm just going to divide through by t plus 2 because I want it in the correct format. So that gives us dv over dt plus 3v over t plus 2 equals k minus 3 over t plus 2. Now let's try and work out our integrating factor. So integrating factor is going to be e to the power of the integral, and I'm looking at this bit here. It's kind of this here, 3 over t plus 2. And this time it's with respect to time that I'm integrating it. So this is going to be a log integral. We get e to the power of 3 natural log of t plus 2. And that gives us e to the natural log of t plus 2 cubed. And the e to the power of natural log breaks itself up. So we get t plus 2 cubed. That's our integrating factor. So we're going to multiply through by our integrating factor times t plus 2 cubed. Now what does that give us? That gives us this, t plus 2 cubed dv over dt plus 3v t plus 2 squared equals k times t plus 2, that's a weird k, t plus 2 cubed minus 3 t plus 2 squared. And now we're ready to get it into the form that we can integrate, so let's collect together the correct parts on the right hand side. So I think we're going to have this v times t plus 2 cubed, and I'm finding the derivative of that with respect to time, and that equals the right hand side k t plus 2 cubed minus 3 t plus 2 squared. And now we can go ahead and integrate this. So when we integrate this, we get this v times t plus 2 cubed equals, and integrating this, we're going to increase the power by 1, so t plus 2 to the power of 4, and then divide by the new power, so that gives us k over 4. And this one here, we're going to increase the power by 1, so t plus 2 to the power of 3, and then divide by the new power, so that divides by 3, so we get minus that, and we get a plus c here. Now I'm looking at my answer, and I'm comparing it to what they've got in the on the question. I seem to have this bit correct, and I feel like I would get the minus 1 as well, as long as I went and divided through by the t plus 2 cubed. But I'm just looking at this final bit here, and I'm having a think about how they got that. So I need to just jump back to the beginning of the question and see if there are any initial conditions I can use. It says that the raindrop falls from rest, and I guess that's at the start of time. So we're going to say that when t is 0, when t equals 0, our velocity is also 0, and then we're going to substitute those into the equation that we've already got. If we do that, that gives us, well, 0 equals 4k minus, and then I'm just looking at this bit, so we'll put a 0 in there, we're going to get 8 plus c. That gives us then c is equal to 8 minus 4k. And maybe if we factorize this, we'd get 4 times 2 minus k. I'm just looking at that because I'm sort of keeping an eye on what they've got in the question here. So now we're ready to write down the next step. So v times t plus 2 cubed equals k over 4 t plus 2 to the power of 4 minus t plus 2 cubed plus 4 bracket 2 minus k. And then I think we're there. We just need to divide through now by t plus 2 to the power of 3. T plus 2 to the power of 3. And that gives us the answer I think we're looking for. So v equals k over 4 t plus 2 minus 1 plus 4 2 minus k over t plus 2 cubed. Because it is a question that says show that, you should be showing every step of your working, because you do not know what the exam board wants to give you a full mark. So make sure you show every step of your working. So that's the first part of this question. Okay, so this question then continues, and we want to find some values. So it says find the velocity of the raindrop 5 seconds after it starts to fall, and we have some other conditions here when v is 4, t is equal to 2. So we just need to put these values in. We'll put the 4 in for v, and we'll put the t equals 2 in. So we get k over 4 times 2 plus 2 minus 1 plus 4 times 2 minus k over 2 plus 2 cubed. If you go ahead and solve this, you should get k as equaling 5.2. And then it says substitute a 5 in. So when t is 5, our velocity is equal to 5.2 over 4 times 5 plus 2 minus 1 plus 4 times 2 minus k over 5 plus 2 cubed. And if we type that in our calculator, we get 8.06 meters per second. Now, all of the substitutions and stuff here, I would say, are really important, because it's going to be very easy to make a mistake getting your k value here, because there's so many parts to this question. But if you realise there is likelihood that your answers further towards the end of a question are going to be wrong, you should be showing all your substitutions in all the later parts, because then you're going to be getting your method marks later on, even if you've got one of these values wrong. So that's how I would approach a question like this. So that was part B. For part C, comment on the validity of the model for very large values of t. So we could approach this in a number of ways. We could actually just try, like, what about t is 1,000, for instance, just see what happens. You could try t is 10,000, for instance, and see what happens there. I guess this is a raindrop falling from the sky, so we might question surely the raindrop might hit the ground within a certain time frame. Other things that might happen is the raindrop might hit a terminal velocity, whereas I think this model is constantly increasing the velocity, which is unrealistic. So I think it's to do with the raindrop hitting a terminal velocity or hitting the ground, which is unrealistic. So we would suggest that the model is not valid for large values of t. So I've just typed the equation into Desmos just to see what it looks like, and we've got our graph. It sort of starts with a nice curvy part, and then it does straighten up. So if we were looking at large values of t, I have had to change it so our x value is the t and our y value is the velocity. But if we're looking at large values of t, for instance, t is, I don't know, 400 or something, we're getting our raindrop travelling at 521 meters per second, which might not be realistic. If we continued, I guess we're, to like 6,000 seconds, well, we'd probably have that's not actually going to be possible, but look how fast the speed is here. So that's where they're heading with that final part of the question. So that's the end of the session on solving first order differential equations. We've covered these first three parts of the specification. The remaining parts on second order differential equations I will cover in a future session. So that concludes this video on solving first order differential equations. If you found this video useful and you would like further videos on A-level further maths or A-level maths, do look at the Callum Cymru website, where there are videos for lots of different subjects, not just maths, at both A-level and GCSE level.